SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to the course on finite element method. This is an NPTEL online certification course. So let us begin by expressing our thanks to NPTEL for having the course in the list, and also CET IIT Kharagpur for making all the arrangements for recording the video and editing the video. To start with, let me introduce the team here. So my name is Amit Shah. I am an associate professor in Department of Civil Engineering, IIT Kharagpur. I am one of the instructors of this course. Another instructor of the course is Professor Vishwanath Banerjee, who is also an associate professor in the same department. So in this course, Professor Banerjee will be mostly talking about the theoretical aspects of finite element method, and I'll be discussing mostly the implementation part of that. So the name finite element method, I am sure that many of you have already heard it, and some of you probably are familiar with the method itself. It has been almost 70 years the method was first conceived, and in the last 70 years, significant amount of research and funding went in to develop the method. And today, you name any discipline in engineering and science, finite element methods has its application there. It won't be an exaggeration if I say that it is one of the fascinating things happens. The development of finite element method is one of the fascinating things happen in engineering science, engineering analysis. And with its development, it's changed the course of engineering analysis forever. And this is very evident from the fact that in the last few decades, probably more than 500 books are written on finite element method. If you just simple search finite element method on Google, I'm sure you will get hundreds of thousands of pages. So learning such a method which has application in almost all branches in engineering and science, learning such a method itself is a long journey. And no course can be developed which can cover all aspects of finite element method. So in this course is essentially intended to start the journey and touch upon some of the important aspects of finite element method, so that you have the platform, and on that platform you can learn on your own and go deep into the method, various aspects of the methods, implementation issues, and then you can see yourself what the miracle this method can do. Okay, so this method is, this course is, there are some prerequisites for this course. Prerequisite in the sense, some basic prerequisites, and all of you have this in your UG program, UG curriculum. You need to have solid mechanics, theory of elasticity, some concepts of matrix algebra. All of you probably have structural analysis, and just slightly advanced version of structural analysis we also call direct stiffness method or matrix method of structural analysis. So with this prerequisite, this course will take you to more advanced finite element analysis, the methods which deal with nonlinearity, geometric nonlinearity, then material nonlinearity, other complexity that you may have in the problem. So this is a 12-week course, and every week we'll have 5 lectures, and each lecture is around 25 to 30 minutes. There are 4 aspects that we'll cover in this course. The first thing we'll see why finite element method. Okay, see, you already had structural analysis, you already had matrix method of structural analysis, and you you have seen that with these methods you could analyze some of the structures. But then, given all this, why finite element method? What causes the development of the finite element method? Then, where finite element method, the application areas, and as I just now said, almost all branches of engineering and science, finite element methods has its applications. We'll just see some of the important applications of finite element method in this course. And then, of course, what is finite element method? The most of the part of this course will talk about what is its theoretical aspects, formulations, and then finally how finite element method means. Once we know the theory of finite element method, the formulation, once we know how it is to be implemented to some real life problems. So these are the four aspects we intend to cover in this course. But please remember, these four aspects are not mutually exclusive. It's not that when we talk about what is finite element method, along with that discussion, we also have a discussion on how it can be implemented and what are some implementation issues. So these aspects are not mutually exclusive aspects. Okay, so there will be around 60 lectures on this method. So this is the first week and today is the first lecture. So right from the beginning, let us not jump into the method itself. In the first week, let us understand the premise, let us understand the context of the finite element method. And then probably with this background will give us a better perspective to look into the method and also to look into the formulations and developments that we discuss in the rest of the lectures. Okay. You see, my background is civil engineering, and probably many of you are having background in civil engineering, many of you having the background in mechanical engineering, some of you probably studying mining engineering, some of you aerospace engineering. So we all studying different engineering disciplines, but in spite of that, we all are sitting together and discussing finite element method. You see, we all have one thing very common. As an engineer, the common thing is, at the end of the day, what is our role as an engineer? Our role as an engineer is to find out solution of some real life problem, right? Now, all the time this solution get manifested in the form of some product, right? For instance, there is a river. I need something to cross the river. That's the problem. Okay. So as an engineer, we can build a bridge across the river. So bridge is the physical manifestation of our engineering, right? So similarly, we build machines which make our job easier. So that's a physical manifestation of our research, of our understanding, of our analysis. So at the end of the day, that has to happen, right? Now you see, when you make a product, every product is subjected to different kinds of environment. For instance, if I have a bridge, that bridge is subjected to some kind of environment, for instance, wind load, earthquake load, and that circumstances may not be different when we make a small culvert. Circumstances may not be different when we make a machine. Circumstances may not be different when we make some electronic chip. Circumstances may not be defined when we make, say, automotive engines or pipe network system. So every structure, every product, every engineering product is subjected to different kinds of environment, right? Now, when we build this, when we make this product, that has to be made such that this product, this structure can withstand those environment. That is an important aspect of any design. We need to, for instance, if we are making again, I'll just bring the example of bridge. If we are making the bridge, then what would be the material to be used in the bridge? What would be the, say, if it is a concrete or a steel, if it is concrete, then what would be the grade of the concrete? How much reinforcement to be given in the bridge? So those are the things to be decided before actually making the bridge. We don't just go to the site, we don't just go to the workshop and start making things, we need to have a plan before that. Plan means we need to have a design before that, right? Now, what is the premise of this design? How to decide what should be the size of, what should be the grade of concrete? How to decide what should be the size of some structural component in a machine? That requires an assessment that when this structural system is subjected to a certain kind of environment, or this environment that it has to withstand, when they are subjected to those kind of environment, how this structure may respond. That is a very important aspects of engineering design, analysis and design. So that assessment is important. So if we are making a building for earthquake resistant building, we need to have an understanding how the building may respond when there is an earthquake. Right? If we are building a ship, making a ship which can withstand the web slamming load, or we can withstand the water current load, then we need to understand then how the ship may respond, how the dynamics of the ship may change if it is subjected to, if it encounters certain kinds of wave. So that assessment is important. Now this assessment, the process of assessing this, how a structural system may respond, is called engineering analysis, right? Now, there are some steps in engineering analysis. What are those steps? Suppose I have a physical system. This physical system could be anything. When I say could be anything, I literally mean it could be anything. It could be a building, it could be a bridge, it could be a machine, it could be an electric circuit, it could be an electronic chip, it could be a automotive engine, or anything, right? I have a physical system. I need to understand how this physical system may respond when it is subjected to some kind of environment. That is the problem I have, okay? But you see, because of the non-linearity associated with the problem, because of the complexity associated with the complex boundary conditions, when we analyze a system, we do not take the system as it is. We first idealize the system. We simplify the system. So, for instance, if this is a physical system, then this physical system needs to be idealized. Okay, this is an idealized physical system. For instance, if you have a background in structural analysis or even in strength of material, you already know what is beam. You have already heard the term beam, term column, plates, shales. When we say something is beam, it is an idealization. It is a structural idealization. When we say something as a plate, it is a structural idealization. Nature doesn't understand what is beam, what is plate, what is shell. For nature, everything is a three-dimensional object. It is we engineers have idealized those structural systems as beams, columns, slabs, plates, shells, like this. So first we need to idealize the system, because when we idealize the system, then we actually remove some of the complexity which may not be very relevant in the context of analysis. Okay. Now, once we have that idealized system, then what we do, we need to have a mathematical representation of that idealized system, what we call mathematical model of the idealized system. In test steps, I'm going to demonstrate this through an example, simple example. So once we have a physical system, then idealized physical system, then that idealized system need to be translated, need to be represented through a mathematical model. Now, once we have that mathematical model, then finally we solve that mathematical model, right? And these solutions actually give me the solution of the physical system. We assume it is a solution of the physical system, but actually it is a solution of idealized system. So it is very important that our simplified system, our idealized system, should be as close as possible to the physical system. When I say as close as possible, I prefer to put that phrase undercoat, because as close as possible depends on the context of analysis. What exactly you are looking for the analysis, for what purpose you are doing the analysis, that is important, because some of the features in the physical system may not be relevant when you do one kind of analysis, but may be relevant when you do other kind of analysis for the same physical system, right? So this is important. Now let me give you an example. Let us take gantry crane. Many of you have seen this gantry crane. It is a very common structural system in workshops. So now suppose I want to analyze these beam of this gantry system, this part. Okay. Now, so what is my idealized system for that? Now, this system is now idealized as this. So, this is a beam, this is an idealized system as this. So, it is subjected to some uniformly distributed load. And this uniformly distributed load is because of the self weight of this beam. Then also we are lifting some weight at this point, and that will cause a concentrated load on the beam, and this is the concentrated load. So this is the system. This is the idealization of the loads, and this is, we assume this is hinge support. These supports are assumed to be hinge support. Now this is also an assumption. This is also an idealization of the support. Okay. So this is the idealized system. Now once we have this idealized system, we need to represent this system through equations, right? And this is the equation. You all are familiar with this equation, the equation, Euler boundary equation of elastic lines. You have already seen it. When the m is the bending moment, which is a function of x, E is the Young's modulus of the system, Young's modulus of the cross section, and I is the Young's modulus of the cross section is E, and I is the second moment of area of the cross section. And this is the equation, but this is not just the complete, this equation, this is the domain that x varies from minus a to a plus a. This is minus a, and this is your a plus L. L is the length, and then these are the boundary conditions. So these all together, the equations, then domain, and then the boundary, the conditions at the boundary give us the complete representation, the mathematical representation of this idealized system. Now you all, I am sure, know how to solve it, and you have already seen the solution of this equation. Now once you solve this, what you get say bending moment, say deflected shape of the beam. Say deflected shape of the beam may be like this. Okay, then you may get bending moment diagram. I'm just bending moment diagram of the beam may be like this. Okay, you may get, if you take any cross section in the beam, and this cross section, your bending stress, you will get bending stress. You will get shear stresses on the cross section. If the cross section is rectangular section, then you say shear stresses distribution will be this. So these are the solution of this system. So once you know the bending moment, once you know the shear force, once you know the distribution of bending stress and shear stress across the cross sections, so you have all the parameters that is required for designing this structural component. So this entire step is called analysis. Okay. Now here my intention has not been to show you this particular equation or this particular problem. Here the intention has been to demonstrate the general process we follow in engineering analysis. Okay. Now this has been, as far as this particular problem is concerned, it has been very simple. It is it's a very simple structure. Supports are very simple. Your loading conditions are simple. Boundary conditions are simple, and we could have a solution of this system. But most of the problems that we encounter in real life, they are not as simple as this. Most of the problem we encounter in real life may not be having an equation which describe the response of the entire structure. For instance, if we take a building frame, we know the governing equation for each individual members. We know the governing equations for beams, columns, but then we do not have a governing equations, a partial differential equation, which gives me the response of the entire building frame. Okay. And sometimes we have the equation, but then because of the nonlinearity associated with the equation, because of the complexity associated with the boundary conditions, it may not be possible to have closed form solutions of those systems. Let me give you some example. For instance, these are some engineering problems. For instance, we want to understand. There is always, if you buy a car, there will be a rating, safety rating of the car, okay, and crash rating of the car. So they do crash analysis of the car. There's not any vehicle you take. So if there is a collision takes place, then what happens to the vehicle? We need to understand that before we design the vehicle, right? Suppose we want to design any structure which is subjected to earthquake loading. For instance, suppose there is a bridge and a train is moving on the bridge. As the train moves, train pass through, the stress is generated in the bridge. And what are the stresses generated because of this moving load? There is an offshore structure. Offshore structure generally encounter the wave loading, current loading. Then when they encounter this kind of loading, then what are the stresses generated in different components of these offshore structures, the electronics chip when it is subjected to the kind of environment it is used. Then engines and machines, the fatigue, the continuous operation in engines and machines, what would the fatigue stresses generated in the beam. Electromagnetism, then computational fluid dynamics, how the fluid flows, okay, in different in pipe network systems, or suppose there is a shock wave generated, and then because of the blast, and the shock wave moves and then hits any structure, then how the shock wave moves through here. Once after the moving of the shock wave, once it hits the structure, what damage it may cause in the structure. Then some biomedical problem, like suppose I want to understand what happens to the artery when the blood flows in it. What happens to the human skeleton when we lift a weight. So those things need to be analyzed. These need to be assessed before we actually design this. These all pictures that you can see on your screen, these are the manifestation, right? But this manifestation requires analysis and design, right? Now, so for this kind of problem, solution is not that easy. That easy in the sense you may not be having a single governing equations, and sometimes the governing equations are it's non-linear. You have complicated boundary conditions. So most of the problem we encounter in real life we cannot have a closed form solution for them. So we need to have a method to solve them. Okay. Now, over the years, over many decades, several methods have been developed, and it is still an active research area. We'll talk about that historical aspects as we move on. Okay. Now, but whenever we analyze this physical system, you remember the first thing is to have an idealized model, a simplified model. Second thing is to have a mathematical model, and then we have the solution of this system. Now, in this context, there is a famous quote by, as it goes, all models are wrong, but some are useful. It is a very, very important realization. You see, when we say model, that word itself says that it is not the exact system, right? It is some some idealization, some simplified version of that system. So throughout this process, physical system to idealized system to mathematical model, and then mathematical model to solution, at every step we make some assumptions. We make some assumptions so that our model becomes relatively simpler. But please note, these assumptions are not ad hoc. We cannot make assumptions arbitrarily. These assumptions have to be based on the context of the analysis. Okay, because these assumptions are essentially the limitations of any method, any model. Wherever those assumptions are not applicable, you cannot apply those methods, those models. Okay. So in this logic, essentially, it is not the question that which method is right and which method is wrong, which model is right and which model is wrong. Rather, the governing criteria of choosing a method, choosing a model, is whether this method is useful in the context of this analysis or not. That is a very important thing. And with this, let me introduce a very important term, very important word, approximation. This is not a new word to you. All of you know this word, the meaning of this word, and you have used many times this word, but it has really a very important implication when we use this word in the context of this course or the context of engineering analysis. Before giving you the meaning of this formally, the meaning of this word approximation, let us do some experiment. Okay. Suppose I have an arbitrary area. Now, all the experiments that I am going to do in next few minutes, you all know it. I am just doing it just to make a point, or rather make few points. We have an arbitrary area, and this we need to find out, arbitrary shape, we need to find out what is the area of this arbitrary shape. Now we have a sophisticated gadgets through which we can find out the area, but let us not go into that. Okay, let us find out what could be a very obvious and a crude the way of determining this area. We put the area on a graph paper or make some square grids and then count how many grids, how many square boxes we have, and we know the area of each square box, and then multiplying by the area of each square with the number of square will give you the area. Please note, if I say that if I multiply this area of this square by the number of square will give the area, that statement is a wrong statement. That will not give the area. That will give an approximate area. That area, that estimation is an approximation of the actual area, right? What next we can do? We can use the finer grid, and then we can even use more finer grid. So in this we have approximation 1 or area 1. In this we'll have area 2, and in this gate we'll have area 3. So as we refine this grid, then we'll have area 4, area 5 and so on. At the different level of refinement, we will move towards the actual area, but every time we will get an approximate area. Actual area will get in a limit sense when the square grid size of the square is extremely small, is an infinitesimally small square, or the number of squares are infinite. Okay, in that limit case it will give you the actual area, but other than that, when you have a finite number of squares, finite size of square, then that always give me the approximate area. You can improve the approximation. You can improve the approximation by using finite grid, but always whatever you get will remain as an approximation. Let's take one more example. This is again, suppose I want to find out circumference of a circle, 2 pi r. We all know it, but let us not go into that. Suppose numerically I want to find out. Okay. So, one method could be divide the entire circle into small segments like this. You can see the animation here. And then once you have these segments, then you calculate the length of each segment and multiply with the number of segments, you will get the circumference. Okay. Now this figure is important. This figure, you see, if we keep on increasing the number of segments, okay, then how the area, how this how this error is continuously how the error continuously reduces. Okay. Now if you take n is equal to 100, your error will be 10 to the minus 4 order, 1000 error 10 to the minus 5 order, 10,000 minus 7 order, then 100,000 it will be 10 to the minus 9 order. And if you keep on increasing the number of segment, you will get your error will be less. Okay. And in the limit case, when the number of segments infinite, then you will get the error almost 0, right, or 0 in a limit case. But other than that, when you have a finite number of these segments, finite size of these segments, always you get the circumference which is an approximation of the actual circumference. Okay. Now, this example, this experiment and the previous experiment, there are few things to take from this experiment. Okay, and that will constitute the premise of our next discussion. What is finite? I mean, in this context, then we'll see what is finite element method, at least the philosophy of finite element method. The first thing is, for the time being, forget about that. We know how to calculate the circumference. It is 2 pi r, and we have gadgets to find out the shape or area of an arbitrary shape. But if we have to do it numerically, right? In both the cases, what we have done, we divided the entire problem into small part. In the first case, into small square, and the second case into small segments. Okay, such that for each square, for each segment, we have the information. We have the information that we are looking for. For instance, in the first case, we were looking for the area, and when we divided the entire area into small square, we know the area of each square. So that information is available with us. In the second case, we were looking for what is the circumference. So when we divide it into segments, for each segments we know the length. So that information we have. So the problem, if the problem is complicated, divide the problem into small sub problems, such that for each sub problems we have the information which we are looking for, and then assemble them or add them, combine all these sub-problems, information of all these sub-problems to get the solution of the actual problem. We combine the area, we add the area of all squares to get the area of the shape and then we add the area of all segments, to size of the all segments, length of the all segments to get the circumference. This is one thing. And the second thing is, always when we do this, always the results we get essentially is an approximation. There is nothing like exact solution. Okay, it's a myth now. So whatever solution, whenever we use the word solution in this context, I am saying whenever we use the word solution, it is always implied it is an approximation. Okay, and the second and the third thing, that if we keep on increasing the number of sub-problems, in the first case increasing the number of squares, in the second case increasing the number of segments, if we keep on increasing the number of these sub-problems, our approximation becomes better. This is called convergence. We converge towards the actual solution. This is converging towards the actual solution. Okay. So, And the fourth thing is we will reach a stage where if we further increase the number of segments, further increase the number of solution, number of sub problems, we may not get further improvement in the sense, see, if we are calculating the area, this area, if we calculate with 10 to the power minus this order, this is fine with me, right? Suppose if we calculate this with this order, with 0.01 order, with this error, this is fine with me. And this we can achieve by this we can achieve by around 24 segments. But if this is acceptable, this approximation is acceptable to me for the problem, then there is no point in going for 100 or thousands or 10,000 or 100,000 segments, 100,000 sub problems. So at some point in time, we need to stop it. Right? And this stopping stage depends on what level of accuracy, what level of approximation is fine for this problem. So these four important things that we can understand through this experiment. So let us stop here today. Next class we'll continue with this. Thank you.